My name is, hello? Can everyone sit down, please? Thank you. My name is Kris Zacny. I'm one of the session co-chair with Mark Cohen. The session is about human and robotic exploration hardware. So if you would like to hear about this, please stay behind. There is a parallel session going in a room across as well. If you would like to hear both sessions, all these presentations are being recorded. So when you go home and you have problems sleeping, you can always dial in. And
You're right, yeah, and have more problems sleeping. Yeah, hi, I'm Mark Cohen. I'm the co-chair, and I would like to present our first speaker, Kris Zacny of Honeybee Robotics, who will be talking about the Stinger, whatever it is.
Geotechnical tool. Thank you. And actually, Jack Schmidt gave a introduction to this by mentioning one of the instruments that you have to use in situ, and that's a geotechnical tool. I'd like to acknowledge my sort of co-authors from Honeybee, Zach, Mank, Jared Atkinson, Cody, and Magnus, as well as from NASA Ames, Arno Rock, Mario Bullard, and Terry Fong. And I believe Arno and Terry are here in the audience today. So why do we care? This is the first thing. Obviously, every instrument should have this slide. Why do we care? So Apollo 15, when they're driving around, it actually the rover starts sliding down. I believe it got bogged down a little bit, and astronauts actually had to get up and either pry it or move it around. So it was very close to the craters where soil is very fluffy. So trafficability is also not very good. Lunar 2 was a robotic mission on the surface of the moon. It did almost get stuck. They had to put it in reverse and drive out because there were spinning wheels. Opportunity rover, it did get stuck. Fortunately, it had enough juice in the batteries that they essentially put a foot down and managed to drive out by spinning wheels as fast as they could. However, Spirit also fell through into the softer material. The folks were waiting for a bit too long, trying to decide what to do. And during this time, there was not enough battery energy in the batteries to actually drive out. And as a result of the geotechnical problems, this mission ended. So why it ended? It had nothing to do with batteries and so on. It was a geotechnical problem. It got stuck, and solar arrays were not placed in the at the ideal angle towards the sun, and the batteries could not be recharged. From an excavation and mining perspective, you also need geotechnical tools. Any road construction, even prior to doing mining, you go in, you measure the strength of the material, you measure the strength of the soil. Based on this, you design your mining processes, you design how big of the trucks you need, how many tons they can carry, and all of this stuff. So everywhere you go, in civil engineering and construction, trafficability, you need geotechnical tools. So there are essentially two different regimes of geotechnical stuff. The first one is near surface, and near surface is only focused on trafficability because this defines whether you're gonna slip or you're gonna go forward. And for this, you have two fundamental instruments. One is called bevometer. It's pretty big. It's more of a research instrument as opposed to instrument you can put in a field. And a vane cone, something that actually you can use in a field to get some kind of a data. And then you have deep subsurface tools. These will tell you not only about some kind of trafficability, but also whether you can do excavation, how much it's going to take in terms of force, energy, and force. And for this, you have soil cone penetrometer. This is essentially a push cone. You're pushing down. You measure resistance to push. So it's not a rocket science, right? You just push the stuff down. And dynamic cone penetrometer, and this is what a lot of road construction folks are using. They're essentially lifting 15-pound hammer, and they drop it like 100 times. And during this time, the penetrometer goes down, and they measure depth of penetration after every single blow. So it's pretty crude, but the data it gets is really important. Lunokhod, the Soviet teleoperated rover, did have a geotechnical tool. It was called a cone vane. It's a combination between a shear vane and a cone. It would push this down into the soil and turn it to measure shear properties of the soil. We've done literally hundreds of tests. As you will see later on, this wasn't ideal. We tried to combine two different instruments into one. And if you try to do this, obviously the results you're getting are not the best results. So ideally, you would have two separate tools to get the good data. In this case, we got some data. And on the Apollo, they use Apollo self-recording penetrometer. This was manually pressed sort of rod into the soil. And there was a drum placed just above the rod where you had a scribe that would, it was like a needle scribe that would essentially cut right through the soft metal as to measure the force and penetration rate. So again, it was purely mechanical system, no electronics. And it worked actually pretty well. Could we go to 3 minutes, please? Thank you. So this shows astronaut pushing on Apollo 16, Station 4, pushing penetrometer into the soil. In this case, it went all the way down. And that's all they needed to do. Push it down, pull it out, go to the next location, push it down. And that was enough to get a pretty good data. And remember what Jack Schmidt mentioned about dexterity in your spacesuit? Yeah, they had to do push-ups to actually get up, right? You couldn't kneel and like what we do here on Earth. And these are the data, some of the data sets you get, essentially force as a function of penetration rate. And that's all you need. That's all you need to determine how much energy is required to develop an excavation system. So let's look at the Stinner. The motivation for Stinner was that the cone vane that didn't work very well. If you look very closely, what the cone does when you push it in, it compacts the soil. So then when you do the shear, when you rotate these four shear blades, you measure shear stresses of a compacted soil, not of the original soil. That's why you're off by a factor of 4, and that's why Lunokhod data wasn't very good. So this data set and this design motivated our design. So what we did is we took the cone vane, we took a self-recording penetrometer, which is a cone, but what we did is we put a shear vane inside the cone. So if we want to get bearing capacity, we're just pushing the cone down. If we want to measure shear strength, we're pushing the shear out through the cone into the undisturbed soil, and we're rotating it in situ to get actual data. And then once we're done, we pull it back into the cone and we push further to another depth. So this is TRL4, and Dan described to you what TRL means. I hope you all remember. It's essentially at TRL4, we start building hardware and start doing testing. So this is our TRL4. On your left-hand side, you can see the cone and shear vane in a deployed and in a housed conditions. We've done hundreds of tests in GAC-1A, NULHT-2M, GRC-3, BP-1, MMS. So all of these Luna simulants and Highland and Mari simulants, and as well as Mars Mojave simulants. It worked really well. And these are the test data you get. On the left-hand side is a force required to penetrate as a function of depth. And on the right-hand side, you have essentially a torque in inch-pounds as inch-ounces as a function of time. So this tells you shear properties of the soil. And this graph shows a cone index in kPa as a function of soil density for different soil types. And these squares, so all the data behind the colored boxes is a manual derived data from instruments, and the crosses is from our Stinner, so it kind of lines up pretty nicely. And this is for the shear strength as well. There is a pretty good agreement. So right now we are developing a TRL-6 instrument. So this is as far as you go before this thing can be used for an actual mission. The TRL-6 brass board. So if it's 4, we call it the breadboard. It's very simple. If it's TRL-6, we call it the brass board system. So this thing on your right-hand side, it's being built right now. It will be deployed on a NASA Ames KRX-2 rover in Atacama in next spring. This is the rover with a resource prospector drill called, for this particular field deployment, ARADS drill. And we plan to put not only the drill, but also geotechnical instrument and take it in spring to Atacama, to the same location. And we actually looked at how to deploy it, either on the side of a rover, like a buggy mount versus payload mount right in the center. Because of payload accommodation, we're probably gonna do it on a buggy mount on the side. And this is how this is operation. So we're gonna deploy it to the ground. We're gonna push the cone into the soil, move the shear vane out of the cone, rotate it to measure the torque and the shear stress properties of the soil, then move the shear vane back into the cone and propagate another 10 or 20 centimeters into the subsurface. And then after all this thing is done, then we can pull it out and go to the next location. So this is overall volume. It's just 85 centimeters long by 37 centimeters by 20 centimeters. And this is mass breakdown. The actual instrument is only 4 kilograms, but the deployment system, like a feed stage to move it half a meter into the subsurface, and the Z stage to position it down, these are combined, have like 64% of the mass of the entire system. We believe with putting more titanium, aluminum, some composite material, we can actually drop it down by at least a factor of 50%. So something like this could weigh maybe 5 kilograms, which means it could fit on a future either rovers or potentially CLIPS landers, commercial landers. And this is a manually deployed system for potentially astronauts or geotechnical engineers here on Earth. With a gauge, with a display, same principle, but all the robotic stuff is done by a human. And this means the mass drops by a factor of 10. Something like this is going to weigh maybe a kilogram at most. So robotics, is a lot of mass, a lot of volume, but humans are also expensive. So to conclude, Stinnett combines Apollo cone and Luna cone vane into one. So it's a nice combination. Side-by-side testing revealed that Stinnett is actually better as a geotechnical tool, provides better results, more consistent results. It is, everyone is worried about dust, and we've been also worried about dust. But in all our testing, the Stinnett and prior prototypes, our shear vane never got jammed by dust. It's more precise and more accurate, and right now we're developing a TRL-6 system for deployment on the rover. And with this, thank you, and that's me in the Bonnie Dunes, and that's Pascal Lee behind me right there. And Bill Pascal is talking in another session right now. So with this, I'd like to open a session to questions. Thank you. No questions? Okay.
Why the Atacama?
We actually piggybacking on another P-Star project that is going to Atacama. So we went there probably in the past 2 years every year. It's more of an astrobiology sort of field deployment. And we thought, well, if the rover is already going there, might as well put more instruments and do more, more science.
Are you worried about the compaction in the desert soils?
Yeah. It's I've been there. I drilled into this stuff. It's really hard, and so it's good or it's bad, right? And where geotechnical tool comes handy is if you stop, it's a data point,
Yeah.
right? It's a data point. This means it's harder than so much, and at that point, you can make decision whether to actually go ahead and mine the site or bring a drilling system and perform additional measurements. Bottom line is there is a point at which any pounding or pushing cone is going to get stopped.
Yeah.
And at that point, you have to bring a drill. But that's a data point.
You're going to trench alongside where you try to...
Yeah, we do trenching as well for not only geotechnical, but also for astrobiology. So we're looking at getting samples from a drill and getting samples with a scoop deployed by a human being and see if we have cross-contamination and things like that.
Okay, very good.
Thank you. Yeah. Right, great, thank you.